Let's say that on a problem, on a test or something, you had the square root of 12 plus the square root of 27. Okay? Now, these are kind of, you can just see immediately they're different entities, and you can't really add them up without doing some work first. So don't fall into the trap of trying to add 12 to 27 and come up with something else under the radical. You can't add radicals like that. You have to do some simplification first. So let's go ahead and do that. If we were to simplify this radical, just like we learned how to do in the previous section, how would we do it? Well, we know that 12 is 3 times 4. And we also know that 4 is 2 times 2. And everything is, this is about as simple as we can get. So we're going to look for pairs below the dotted line. Of course, we have a nice pair here, okay, the 2. So we're going to take this 2, we're going to pull it out, and the 3 is by itself, so it stays in. So this reduces to 2 times the square root of 3. Everything we've done here is the kind of thing that we learned how to do in the previous section of the class. So let's keep that right there. Separately, let's go ahead and try to reduce this. 27 is 9 times 3, right? And 9 is just simply 3 times 3. And that's as simple as we can go. So we're going to start to look for pairs here. Of course, we've got a nice pair right there. So we're going to pull the 3 out, and we're going to say that the square root of 27 is equal to 3 times the square root of 3, because we have a lonely 3 here left over. There's nobody to pair up with 3, so it has to stay underneath the radical. So we have reduced the problem from something that looks unfriendly and different to something that looks, believe it or not, it looks a little bit better. Because notice here, in the first term, I have 2 times the square root of 3. In the second term, I have 3 times the square root of 3. I'm going to tell you what the answer is, and then we're going to talk about why. This is going to equal 5 times the square root of 3. Okay? And let me explain really why that is. If you remember back to the first DVD that I produced on algebra, when we learned how to just simplify terms in an equation, if you have something like x plus 3x, what is the answer here? The answer is that this is equal to 4x. And the reason why is because here, x is just a number. It's some quantity. X can be pencils, for instance. It's easier for you to think about it in terms of pencils, if you ask me. So here I have x number of pencils. Here I have 3 times x number of pencils. So I have 3 times as many pencils here on this side. So when I add them together, I've just added the number of pencils I have, which I don't know how many I have because it's a variable, but you have x units of something and 3x units of something. So when you add them together, you just get 4 times x units of something. Okay, x is the variable, okay, in that expression there, or the unknown. Here, it's exactly the same. Here I have 2 units of a quantity that I'm going to call square root of 3. It just happens that square root of 3 is a number. You can put it in your calculator and you can find that it is a number. Here I have 3 units of square root of 3, which is just, again, some number. So here this term is common with this term. And that's why you can add the coefficients in the front and arrive at this. I have 2 units of square root of 3, 3 units of square root of 3. I add them up, I get 5 units of square root of 3. It's exactly the same as this. Okay? So the bottom line is when you do these kinds of problems, what you're going to do is you're going to simplify them. You're going to get them into some form, and hopefully you'll have something common like this that will let you add them together. If you don't have any commonality, well, you just can't add them up. At least you can't add them up and get a nice answer in terms of a radical. You can always put it in your calculator and calculate some decimal, but as far as getting a nice pretty answer for a test, it's not going to happen unless you get that done. So let's say you had square root of 48 plus the square root of 75. So just mechanically following through, this is 12 times 4 gives me 48. 3 times 4 gives me 12. 2 times 2 gives me 4. And over here, again, I have 2 times 2 gives me 4. And I'm going to be looking for pairs underneath this dotted line because that's the bottom of the tree. Okay? we'll use some color here to make things easier to see. We have one pair here. We have another pair here. 3 is all by himself. He doesn't have a pair. So I'm going to take 1 2 out over here because of this pair. I'm going to take another 2 out because of that pair. Of course, they're multiplied together because they're just hanging out by themselves. Times the square root of 3. 3 stays under the radical because it has no pair. This reduces to 4 times the square root of 3. Okay? So not too bad so far. This guy is 25 times 3 gives me 75, and 25 is simply 5 times 5. So if I'm looking for pairs, of course I've got a nice 5 here. I'm going to just write this down here. The answer here, I'm going to pull the 5 out. That's going to give me 5 times the square root of 3. Okay? Actually, I'm going to write it right here. So, we've taken this square root of 48 and we've done our magic. We've arrived at 4 times the square root of 3. Okay? We've taken the square root of 75 and we've reduced it down to 5 times the square root of 3, all using the same method that we learned in the previous section. And then here, you notice your common term is a square root of 3, which behaves just like the variable x in an equation. And so I've got 4 units of square root of 3, 5 units of square root of 3, or pencils if you like. And so in the end, 4 plus 5 is 9 times the square root of 3. And that's the answer to that problem. Okay, let's do one with a subtraction. Let's say you have square root of 18 minus square root of 8. Again, 18 is 9 times 2. 9 is 3 times 3. So here I'm going to look for a pair. I've got one there. I'm going to pull that 3 out. That gives me 3 times the square root of 2. For the 8, it's 2 times 4. For the 4, it's 2 times 2. So I'm going to look for a pair. I have it. I'm going to take this 2, I'm going to pull it out. So it's going to be 2 times the square root of 2, which is just left over. It just stays under the radical. And these two quantities are subtracted from another. So I've got 3 square root of 2's, 2 square root of 2's. So these are common, so I can just subtract the coefficients. 3 times 2 is 1 times the square root of 2, which is just simply the square root of 2. That's pretty much it. Now here's another problem here that's kind of interesting, and you'll see why in a second. If you have the square root of 9 minus the square root of 50, let's try to simplify this. Square root of 9 is 3 times 3, which is the only thing there, and it's a pair. So the answer to the square root of 9 is just 3. And that makes sense, because 3 times 3 is 9. And that's the definition of a square root. 50 is 10 times 5, okay? And 10 is 2 times 5. Okay? So if I'm looking for a pair here, here's a pair right here. Okay, because these are the lowest portions of the tree. 10 doesn't participate because it's up in the tree. You only look at the bottom parts of the tree here for your pairs. So this is the 5 is gonna be pulled out. I'm gonna have 5 times the square root of 2. That's the answer for this. We already found that the square root of 9 is 3, and now I need to subtract those two. Okay. What do you think we should do here? Well, we have a square root of 2 here. There is no square root of 2 here. There's no way to make this 3 any simpler. It's just a number. You can't do anything with it. This is already fully simplified. There's nothing else to do with it here. So this, if you had a test, would be your answer. There is no way to simplify this anymore. In order to add or subtract radicals, you have to have a common radical in there. It's just like you know x plus 3x is 4x, okay? But if you have x squared plus 3x, well, what's that equal to? Well, you can't do anything here because x squared is a term, 3x is a term, and there's no commonality in x here. So you can't just ignore the fact that this is a square. You just can't add them. So in this example, this is as simple as you can get. You just can't do anything more with it. Same thing here. You can't do anything more with it because it's already in the simplest form. So just remember that when you try to simplify these things, you have to have something common. Okay? Let's work on a problem that's a little bit different. 2x squared, I'm going to have a square root here, plus square root 8x squared. And we want to do the simplification. Well, for 2x squared, that's 2 times x squared. And for x squared, it's just going to equal x times x, right? So again, I'm looking for pairs underneath the line, and I found one here. So I'm going to pull the x out. It's going to give me x times the square root of 2. Okay? Likewise here, this is going to be 8 times x squared. Okay? 8 is just simply 2 times 4. 4 is just simply 2 times 2. I can't do anything more with that. And x is just x times x. So again, I'm going to look for pairs underneath the dotted line because that's the bottom of the tree. I found a pair right here. 2 is a pair and x is a pair. The 2 is going to come out like this. And x is going to come out because it's a pair like this. And underneath the radical, I'm going to be left with square root of 2 because it's left over. And these are added together. So what I have here is x times the square root of 2 plus 2x times the square root of 2. What does this equal? Okay. Well, notice here, in this case, x times the square root of 2 is some term. Over here, I've also got an x times the square root of 2. So here, this is kind of common to this. So this is a common subterm of this expression right here. So in order to add them, all I need to do is look at the coefficients. 2 is a coefficient here. 1 is a coefficient here. So 1 plus 2 is 3 times x square root of 2. Let's do one a little bit more complicated. What if you have 18 times x squared times y? All this stuff is under the square root. Minus 27x squared y. All this stuff is under the square root, and I'm going to subtract these two numbers. So again, all I do is I plow through it. I try to simplify, I see what I get. This is going to be 18 times x squared times y. 18 is 9 times 2. 9 is 3 times 3. X squared is x times x. So the bottom of the tree here is everything like this. That's the bottom of the tree there. Okay? So if you look, I've got one pair here, another pair here. So a 3 is going to come out, and x is going to come out of the radical. Underneath the radical, I'm left with a 2 times a y, because there's no pair there, so it has to stay inside. Okay? So that's done with that part of the problem. What about this one? This is 27 times x squared times y. Okay? 27 is 9 times 3, and 9 is just simply 3 times 3. And x squared is simply x times x. Okay? So, underneath this is the bottom of the tree, so we're going to look for pairs right there. This is a pair. This is a pair. Okay? So the 3 comes out. And we're subtracting these quantities, so I'm going to put a minus sign. 3 comes out. X comes out. Underneath the radical, I'm left with a 3y. Okay? I'm left with a 3y. And that's really, about as far as you can go. I mean, you don't have much commonality here. The only commonality you really have is the 3x and a 3x here. So really, if you wanted to go any more with this, the only thing you could do is you could factor out 3x and say it's 2. You could say it's the square root of 2y minus square root of 3y. You could do that and factor out 3x, because if you think about it, if you distribute this back in, 3x times square root of 2y gives you this. 3x times this quantity here gives you this. That's where you started from. But you can't really just add these terms together because you've got this common. But when in the other case, we had like when you have x squared plus 2x squared. Well, this is common, so I add the coefficients. So I can add 1 plus 2 and get 3, and it becomes 3x squared. Well, that looks great, okay? Here, I have this common with this, so I add the coefficients, which are basically these terms. But when you do that, you really can't simplify much. So you really can't simplify this very much. But you can factor out the 3x and arrive at this answer right here. Notice that you can't subtract these. You can't do anything more with this because they're completely different under the radical. This would be like x, and this would be like x to the 5th power. They're just different things. You can't subtract them. And really, my opinion is either one of those answers is probably equally acceptable. I mean, some teachers might like to see you factor it out, factor things as much as you can, but in reality, they're the same exact thing, and it's arguable if one is really any easier to, or any more simplified than the other. Let's talk a little bit about cubed roots. Cubed root, it has a square root symbol with a 3 at the top. That's supposed to mean cubed root. And I'm going to explain a little bit more about what I mean by that here in a second. Okay? When you write the regular square root symbol, this means square root. Well, there's kind of an implied 2 up here. This doesn't mean anything's raised to the 2nd power. It's just reminding you it's a square root. It means that, when you have this implied 2, it means that if you have like, 9 in here, and you go 3 times 3, this 2, the square root, the word square, means that when you do this trick with the tree, you look for pairs of 2. So in this case, I have a pair of 3s, so I can pull out one of those 3s and pull it out of the radical sign. And, that's fine and dandy, okay? When you have a cubed root, okay, that means that whenever you do your tree, you don't look for pairs of 2, you look for pairs of 3. That's really all it means. And the reason is, the definition of a square root means that whatever number you get, when you multiply it by itself 2 times, gives you what's inside. Like the square root of 9 is simply 3. That's because 3 times 3 equals 9. That's why. That's why you're pulling pairs of 2 out, because 3 times 3 is equal to 9. Over in this case, with the cube root, 27 is 9 times 3, and 9 is 3 times 3. So you can see that we have, it's not really a pair, but it's just a grouping of 3. The cube part means look for sets of 3. When you find one, pull it out of the radical. There's nothing left over, so there's nothing underneath the radical. You pull this 3 out, and that's it. That's the answer. So the cubed root of 27 is 3. And to prove that to yourself, the definition of a cubed root means whatever the answer is, 3 times 3 times 3, you multiply it by itself 3 times instead of 2, but 3 times, this equals 27. And you can just see 3 times 3 is 9, 9 times 3 is 27. So the only difference, big picture, is that when you're working with cube roots, you just look for groupings of 3. And then you do the exact same technique we did with the square roots. It's the same thing, same story. Nothing else has changed. You just look for groupings of 3. So let's do that. For 16, 8 times 2 is 16. 2 times 4 is 8. And last but not least, 2 times 2 is 4. So I'm looking for groupings of 3 in the bottom of the tree. Okay? And look here, I found a grouping of 3. Okay? So I take this 2, because I found a grouping of 3, I pull it out. So this is 2 times the cubed root of 2. 2 stays inside the radical because it's left over. It has no grouping of 3 associated with it. It's lonesome. Okay? But when you put the radical around it, you have to put a cubed root symbol because that's what you started with. Other than that, it's exactly the same as before. For 54, 9 times 6 is 54. For 9, 3 times 3 is 9. And for 6, 2 times 3 is 6. And of course, you have a pair here. It's not really a pair, it's a grouping of 3. So I take the 3, I pull it out like this, and inside I'm left with the cube root of 2 because 2 is left over. Okay? Now, it becomes simple. I've got cube root of 2 common here, and I've got a cube root of 2 common there. So that's my common term. I'm just going to add the coefficients. 2 plus 3 is 5 times the cube root of 2. That's the answer. So you can see cube roots really aren't that big of a deal. We'll do one more problem in this section and we'll move on. Let's say you have the cube root of 81 minus the cube root of 24. Well, for 81, 9 times 9 is 81. And then we've got 3 times 3 for each of these. Okay? Now I'm looking for groupings of 3 because it's a cube root. I found one right here. So the 3 goes out, and I'm left with the cube root of 3 on the inside because 3 is lonesome by himself, minus, because we're subtracting here. 6 times 4 is 24. 2 times 3 gives me 6. And over here, 2 times 2 gives me 4. Okay? And I found that I have a grouping of 3 right here. So the 2 comes out. Inside, I'm left with the cube root of 3, because that's lonesome, it's left over. Now look what I have here. I've got cube root of 3, and I've got cube root of 3. They're common terms. So I'm just going to end up subtracting these coefficients here. 3 minus 2 is 1. So I'm going to have 1 times the cube root of 3